Welcome to another lesson of transparent physics. This one is about solving nuclear equations. And I find when I teach this in my classes, it can be pretty challenging. There's a couple areas where it's easy to trip up on. So we'll go through it nice and methodically. And by the time you're done, you'll be able to discuss the decay products alpha, beta, gamma for any isotope you wish. So, life of the party. Okay, a little bit of new vocabulary here to start. When a radioactive isotope decays, its product has a sort of a traditional name. It's known as the daughter product. And the daughter product is whatever you get when that isotope undergoes decay. And when we are looking at a problem, what we are interested in is we are interested in a relationship between the original isotope and the daughter product. And in a nuclear equation like the ones we're going to be talking about for this particular lesson, that combination occurs with some sort of radioactive emission. In an earlier lesson, we talked about alpha, beta, and gamma. Now, these are not the exclusive ways by which radioactive events occur, but at an introductory level, alpha, beta, gamma are a pretty good starting point for most of what we would need to worry about. Remember, beta is beta plus and beta minus. So, now that we're getting ready to talk about the general format for a nuclear equation, here's where we sort of break into some new stuff. So probably a good time to pause. Have a nice cup of tea there for a second. And let's get into this. Now, this is my technique that I've developed over the years. I'm not saying other people don't do it a little differently. And I'm not even saying that if you go in and talk to somebody who's really high level on this stuff, that they might not be like, well, I don't know about that. What I find is this technique is the fastest way to get people where they need to be when they need to start looking at these nuclear equations. So let's take a look at a generic equation. And so we have W. These letters, it doesn't really matter. Just W is what I'll consider to be the original isotope. And then the original isotope, actually I have an equal sign there. Really, it's normally written as an arrow sign more than an equal sign. So we'll just change that right now. All right. So the idea is that the original isotope decays into, that's what this arrow stands for, decays into. All right. So we start with this. We go to this. This is whatever the daughter product is. And then we have some sort of radiation emission. It could be matter, it could be energy. Now, there are numbers on the top and the bottom. I'll show you some examples of that. Generally speaking, what we need to remember is I consider the number at the top to represent kind of particles with mass in the nucleus. Of the ones that we talk about, protons, neutrons, and electrons, it's only protons and neutrons that have notable and significant mass. Electrons technically do have mass, but they are it takes about 2,000 electrons to equal a proton or a neutron, so they generally don't factor in much. And on top of that, we are talking about nuclear equations. So nuclear equations deal with the nucleus. Electrons in general aren't to be found in the nucleus, although if you've been paying attention, you know the exception to that. And so we just worry about the stuff that's in the nucleus right now. The numbers on the bottom, there's different ways to think about these. I have found it's useful to think of it in terms of like a charge. And again, it's the charge of the particles that are either in the nucleus or ejected from the nucleus. The particles of note with charge, protons are plus ones, electrons are minus ones. We can get other things in like the positron and stuff like that. So both these sort of fall within the lines of conservation laws. You've talked about conservation laws in your other science classes. The top one is basically what I consider to be a conservation of mass argument. Matter is neither created nor destroyed. And the bottom argument is a conservation of charge argument, which means if you have a certain amount of positive charge to start, that same amount of charge needs to be represented at the end. You can't magically create a negative charge out of nowhere, things like that. All right. Now, a little review from a previous lesson. The options on the menu. Now, sometimes it seems like you want to pick something else, but generally speaking, you've got these three options to work with when trying to figure out what goes on radiation-wise. First of all, there's the alpha particle. Remember, the alpha particle is a helium nucleus, so it is sometimes written as He or it's sometimes written as alpha. And you can see these numbers here correspond. Oh, here, I tell you what. These core numbers correspond with the same sort of idea that I was talking about before. So the mass of the helium nucleus is 4, means 2 protons and 2 neutrons, and it has a +2 charge associated with it because of the 2 protons. The neutrons don't factor in. Okay, that's the alpha particle. Technically, there are 2 flavors of beta. The beta minus. Beta minus has effectively, we consider it to have no mass nuclear-wise because the mass is so much smaller than the proton and the neutron. There's a -1 charge associated with it. It is sometimes written as an E for electron or sometimes written as the B for beta particle. Technically, every time we do this, there is an electron antineutrino, but there's no mass, no charge associated with that as far as we're concerned. It's just kind of in the mix. So sometimes I'll write it. I usually don't worry about it at an introductory level because it doesn't affect the big numbers. It's just something that when you know more about it, you know that it should be there to make sure everything sort of balances out. And the partner to beta plus or partner to beta minus is beta plus. Again, it's a beta minus is an electron, beta plus is a positron. Just like an electron, identical to an electron, except it is positive where the electron's negative. Write it the same way, -1 +1, go from there. Now also there is the gamma ray. I'm not going to really show you any examples with gamma rays here. Gamma rays they're important and they're like legit and stuff like that, but as far as our calculations go, you can see they have no mass and they have no charge. So the argument here is that a gamma ray, if you remember from our earlier video, is really just a way for the nucleus to kind of blow off some steam, but it's the same nucleus afterwards as it was before. I can't think of a gamma decay particle off the top of my head, but any isotope that decays with a gamma ray is the same isotope afterwards, it just has less energy. So calculation-wise, it's kind of a moot point for what we need to do for today. Important to remember. I trim my words a little bit just to keep it clean here, so I do apologize for the little scribbly there, but let's just focus on the things around it. So, are the masses the same on both sides? Are the charges the same on both sides? If you've conserved your mass and you've conserved your charge, then you've done what you're supposed to do. So let's hop into it. Let's see a couple examples of this. We'll work our way through, and hopefully by the end you will be pretty comfortable with the process of solving a nuclear equation. And I'll just give you some of my tips and techniques on how to do this. So let's take a look here. Alright, so example number 1. And we want to ask ourselves the following question. What isotope results from the alpha decay of gold 185? Now, remember the way it's phrased like this, gold is our element. And then 185, think to yourself before I say it for a second, is the atomic mass. Okay, the mass includes the number of protons and the neutrons. So this specifies the specific isotope of gold. Now, what's the atomic number of gold? I don't have it memorized. We'll use a periodic table to figure that out. Okay, so the general format is we're looking at an alpha decay of gold 185. So the isotope that results from it is the daughter product. So I can break out a periodic table. My physics textbook actually has a periodic table in it. So a hint for you. When you're trying to find stuff on the periodic table and you don't really know what the atomic number is, like where is gold exactly on the periodic table, start taking a look at the atomic masses. You'll see them listed. Once you find a zone that's around 180 something, you're in the range of around gold. I'll show you what I mean here. For example, so I don't know where gold is exactly, but I know that this question has an atomic mass of 185. So I put this back into place, and I start asking myself, where's around 185? So here's 183, 186. So 185's got to be around here somewhere, and there we are. So gold has an atomic number of 79. All right, so this is a lighter isotope of gold, it looks like. All right, so the way I write that down is I say gold. It's our initial particle, and we are looking at the idea of gold having an atomic number of 79. 79 goes on the bottom because that's the amount of positive. It specifies that we are talking about gold 185. 185 is the total mass of that nucleus. Now gold 185 decays into something that we don't know. And they do tell us that it's an alpha decay. So an alpha decay is written like this. 4 on the top, 2 on the bottom. 4 represents 2 protons and 2 neutrons. 2 represents 2 protons. And then what you want to ask yourself is, okay, what's going on here? What goes right here? And you can sort of imagine 2 empty spaces that we need to fill. Once we have those spaces filled, we know exactly what we're dealing with. So over here, we just want to ask ourselves conservation issues. So we have 185 has to equal some number plus 4. All right, so 185 plus one number, so that's got to be 181. 181 makes that statement true. On the bottom, we have 79, and we have 2. So 79 and 2, the answer to that is 77. So we're going to take a quick look at our periodic table and see if we can figure out what numbers make those balance out. All right, so let's break on our periodic table here and see what we can see. Now, we know that we have to find something that has an atomic number of 77, atomic weight around 181. So we break out our periodic table here. 77, right here, iridium. All right, and that getting a little lighter than we would expect. See if we got that down right, but 77 is again IR. All right, so iridium 77, atomic number 181. All right, and that's how we do it. So gold decays into iridium 181 plus an alpha particle. All right, so let's try it again. Number 2. All right, so we got bromine 82 undergoes beta minus decay into what? So again, bromine 82, I'm not going to break out the periodic table every time here, but if we take a look at some of these values here. So bromine, when you take a look at bromine 82, so that's Br. We know it's bromine 82, so 82 goes on the top there. And when we look it up in the periodic table, we see bromine has a positive number of protons, 35 in the nucleus. Now it undergoes beta minus decay, so we have again, an unknown value, and beta minus decay is a 0 at the top, -1, and the electron there. Now again, technically you can write, you can write the little anti-neutrino here if you want to, for consistency's sake. For our concerns, we don't really need to worry about it. All right, so what do we know? We've got these two things to work out here. All right, so we'll do it over here just for consistency's sake. But 82 equals something plus 0. What could that be? Of course, that's 82. Now, this one is a little trickier on the bottom, though. So it's 35, and then equals plus a -1. Now, I do see kids make mistakes on this all the time. Again, math-wise, it's pretty straightforward. If you ask somebody to do that, they'd get it right probably every time. But in this context, kids are going fast, and it's easy to mess up. So what do we have here? Something -1 equals 35, so that has to be 36. That number is extremely important because that tells us what the element is. All right, and 36 is krypton. Okay. Now, again, this is also counterintuitive because when we think of nuclear decay, we think of things getting smaller, things breaking apart. In this case, the atomic number actually goes up by 1. If you remember, the atomic number goes up by 1 because beta minus decay has the neutron that splits into a proton and an electron. So the neutron turns into a proton, not changing our total number of particles in the nucleus, but causing the atomic number to go up by 1 because we have 1 more proton than we did before. And then we spit out that electron. Okay, nice. All right, example 3. We're going to have 6 examples total. So by the time we're done, you'll see pretty much all kinds of things that you would need to know to be ready to go. All right, nitrogen-13 emits a positron and becomes what? So nitrogen-13, when we look nitrogen up in the periodic table, we would see its atomic number 7. And we have something and a positron. And the antineutrino. Well, in this case, it's a neutrino. Okay. Bracket on the top, bracket on the bottom. Again, not too crazy. 13 equals something plus 0. And 7 equals something plus 1. So the number on the top here has to be a 13. The number on the bottom there is a 6. 6 defines our element. Atomic number 6 is carbon. So this is carbon 13. So nitrogen decays into carbon 13. The number on the bottom tells you the element. The number on the top tells you what the isotope of that element is. Okay, those are the basics. Let's fancy it up a little bit. So we got uranium-233 becomes thorium-229 by what process? So uranium-233, uranium is capital U, and 233. And when you look up uranium, the atomic number is 92. And it turns into thorium, that's TH, 229. You look that up on your periodic table, and you see that thorium is atomic number 90. And then there's some process here. So what particle gets ejected from the uranium nucleus such that when it's done, we're left over with a thorium. So we do our math over here. It's the same process, even if it's a different element of the equation. So 233 equals 229 plus something. And 92 equals 90 plus something. So 229 plus 4 equals 233. And 90 plus 2. So this is going to be a 4 and a 2. And you know what that is. That's an alpha particle. So uranium becomes thorium by alpha decay. All right. Big chunk of the nucleus gets blasted out. All right, example number 5. Again, 2 more and we'll be done. Well, you can be done anytime you want to. I'm not saying, but hey, there's some good stuff. We got a little. Oh, this is a long one. I can't quite fit this one all in. All right, so example number 5. You can know what the example is. We'll slide it over. Okay. What element undergoes beta plus decay to become tellurium-124? Oh, so now we have an unknown at the front. So we don't know what we're starting with. And we are undergoing beta plus decay to become tellurium-124. So tellurium-124 is Te. Atomic number 52. You look that up on the periodic table. You don't have to have that memorized. All right, beta plus decay means you've got a 0 and a plus. And again, you put your neutrino in there if you want to. All right, so the question is, what are we starting with over here? I'm going to send this up a little bit more for argument's sake. All right, so we got unknown and unknown. So something equals 124 plus 0. Not too crazy. And something equals 52 plus a positive 1. Okay, so 124 and 53. So the idea of beta plus decay, if you remember, a proton turns into a neutron and ejects its positive charge as a positron. We don't know what element this is until we look at our periodic table, and 53 is iodine. So the answer to example number 5 is iodine 124. So iodine 124 undergoes beta plus decay to become tellurium 124. Remember, with beta plus and beta minus decay, the atomic mass doesn't change. The total number of protons and neutrons remains the same, just we flip a little bit which ones are protons and which ones are neutrons. Okay, last one's written in the form of a riddle. All right, so the question is, I eject an electron and I turn into sulfur-32. What isotope am I? So as far as riddles go, I don't know. I don't think you'll see that in like The Hobbit or something like that, but yeah, whatever. All right, so we don't know what we're starting with, but something ejects an electron and turns into sulfur-32. Now, sulfur, when you look it up on your periodic table, is atomic number 16. And we eject an electron. Ejecting an electron is beta minus decay. So we want to see what we start with then. All right. So we do our little numbers again last time. So something equals 32 plus 0, and something equals 16 plus a negative 1. So on the top is 32. Again, classic of beta minus and beta plus is the atomic mass doesn't change. 16 minus 1 gets us this. So again, if you're going to screw these problems up, this is probably a good one to mess up. But again, 16 minus 1 is 15. All right? And atomic number 15 is phosphorus, P. Okay, when phosphorus undergoes beta minus decay, if you remember, is a neutron that splits into a proton and an electron. Splitting into a proton increases the atomic number by 1, but not the atomic mass, because the same number of particles in their nucleus. Okay, there we go. That is how to solve nuclear equations. Once you understand the ingredients that you can work with, and as long as you have a periodic table handy, these usually aren't too bad. It's a little bit of basic algebra. The tricky parts, I think, are beta plus and beta minus, because you have to take a little bit extra time to think about how those numbers work out. Again, I didn't show any specific examples of a gamma ray decay because they're not terribly interesting. So if you can work out beta plus, beta minus, and alpha, a gamma ray will offer you no difficulty at all. But hey, I appreciate you taking the time to learn about solving nuclear equations with me. Hopefully with transparent physics, we've made this topic a little clearer.